today we will finish up unit circle trig, and then Tuesday and Wednesday we're going to look at graphing trig functions. The only ones we're going to look at are sine and cosine. Those are the easiest two to graph. And then we'll look at tangent, the cosecant, all the other ones in 6.4. So that'll be next academic week. And we're going to do the same thing we always do with functions. I'm going to show you how to shift them left and right, up and down, stretch them left and right, all the same stuff that we usually do. All right, so last time we did unit circle trig. I told you that you always have to be able to figure out the coordinate, and only angles that I didn't give you coordinates for were 0, 90, 180, and 270. So just as kind of a reminder, what was the coordinate for 0 degrees? Yeah?
2 pi.
A coordinate.
Oh, sorry. 1, 0.
1, 0, and 90 degrees was, yeah?
0, 1.
0, 1, yeah, and so on. Well, I'm going to show you today how do you get the coordinates for a 30, 60, and 45 degree angle. Okay, how do you do those three? And if you can do a 30, a 60, and a 45, then you should be able to do any multiple of 30, 60, and 45. So we'll look at unit circle trig with the 30s, 60s, and 45s. And then might do a little work with trig identities. We'll see. Okay, trig identities are a topic we look at several times, and they kind of introduce it here, but we'll see. All right, so let's start with the 45 degree angle. So the goal is going to be to figure out the x and the y value for 45 degrees. Yeah?
You go back to the very right. And do I put a decimal next to that 6, the 3, and the 4?
No, those aren't decimals. No, fractions. All right, so we can't do anything. Let me just show you the kind of problem. Like that's what I'm going to ask you to do in a minute. Find the sine, the cosine, the tangent, all the stuff we've done with 45 degrees before. But we need the coordinate to be able to do that. All right, so what I'm going to do is, in the circle, I'm going to draw a 45 degree angle. So it's halfway between 0 and 90. And make a triangle out of it. And then we have to figure out how far to the right we go. That's going to be the x. And then how far up. That's going to be the y. Now, we don't know what the x and the y are going to be yet, but they're in a 45, 45, 90 triangle. So how do x and y compare to each other? Yep.
Are they like proportional or inversely proportional or anything like that?
Yeah, they would be proportional. If you change the size of the triangle, they would change together. Yeah.
They're equal.
They're equal. It's a 45, 45, 90. That's an isosceles triangle. So whatever x is, that's what y is. Okay. So let's see if we can find it. Got the same triangle down here, just a little bit bigger, so I can do some work. All right. Well, one side of this triangle we already know. What side do I know in that triangle? Yeah. Yeah. What's the hypotenuse? 1. Well, what's the theorem that we can use in a right triangle to find a side if we don't know it? Yeah.
Pythagorean theorem?
Yeah, let's use the Pythagorean theorem. Now, I don't know either one of these sides, so I need to pick a letter. I'm just going to call the bottom x. Since it's isosceles, technically that means the height would be what? That would also be x. I don't want to use a different letter because it's not really a different value. It is the same value. Okay, so let's solve for it. What would Pythagorean theorem look like if you set it up for that triangle? About Richard, yeah.
X squared plus x squared equals 1.
Yep, x squared plus x squared equals 1. So we get 2x squared equals 1. Solve for x squared. Okay, what do I have to do to get x squared by itself now? Yeah?
Forgot the name of it, but square root.
Square root. So remember, when you square root a fraction, you do the top and the bottom separate. So that's 1 over the square root of 2. And what would that simplify to if we get the square root out of the bottom? Yeah.
Square root 2 over 2.
Perfect. And that is the length of each side in a 45, 45, 90. Square root 2 over 2. Okay, so I'm going to go back up, and I'm just going to label my triangle. So this side is square root 2 over 2. So that's how far right. And the green side is also square root 2 over 2. That's how far up. So what do you think the coordinate would be for 45 degrees? Yeah. Square root 2 over 2, comma, square root 2 over 2. Exactly. Now that we know that's the coordinate, we never have to find that again. We just want to remember square root 2 over 2, square root 2 over 2. That is always the coordinate for a 45-degree angle on the unit circle. Okay. So any question on finding that one?
Just go.
So really just use Pythagorean theorem. Now we're going to do the 30 and the 60. And they're connected. So once you do the 30, you automatically have the 60. You'll see how they're connected. Okay. So let's get the 30 and 60 out of the way, and then we'll start doing some trig problems. Okay. Is this an isosceles triangle?
No.
But I can't do the same trick I did last time. I can't label each side the same letter because it's not isosceles. So they're all different. Well, the problem is if they're all different lengths, we do know one side. What side would I know if this was in a unit circle? Yeah, it would be, it would look something like this in the circle. And there's a bigger version. How long is the hypotenuse? 1. It's the radius of the circle. You can't use Pythagorean theorem until you find one of these other sides a different way. Okay, I'm going to give you a hint at how to do it. It's kind of a visual trick. Let me group all that together. And I'll just put that there for a second. Does anybody have an idea of something I can do? Yep.
But you could combine them into one bigger triangle.
Which way?
So that way that one's like flipped upside down. So that way the 60 degrees is pointing down instead of up.
Okay, so take this and do a flip. Like that?
Yep. And then yeah, like that, and then you combine them.
Now, by doing that, what did you just look at the big triangle?
Isosceles. Well, not the right triangle, not the isosceles, but all the sides are equal, which is another type of triangle.
Yeah, what did we create there? Yeah. This is an equilateral triangle. So this side is 1, this side is 1, but more importantly, this side from here to here is also 1. But what do you know about the red side and the blue side? Yeah?
They're half of each. Half of one. They're equal to each other.
They're equal to each other, right? Because they're mirror images, right? So the red and the blue side are equal. So together, the red and the blue side add up to 1. And they're equal. So that means each one of them has to be how much?
Half.
A half. Exactly. Now, we can use the Pythagorean theorem to find the third side. Okay? We figured out that other side using a little trick. Okay? I don't need the bottom triangle anymore. Yeah.
How do we know that that piece equals 1 and that whole thing?
Because it's the radius of a unit circle.
Well, the hypotenuse is 1.
Oh, and this is true. When I had this,
Like,
well, this is an equilateral triangle,
oh,
60, 60,
right,
60.
okay.
So if all the angles are the same, then all the sides are the same.
Yeah.
Yeah. Okay, and now I don't need the bottom triangle anymore. Let's just focus on the top one. Bless you. Call that x and use Pythagorean theorem to find it. All right. Can someone set up my Pythagorean theorem using the numbers I have there? Yeah.
X squared plus 1/2 squared equals 1 squared.
Okay. So x squared
Plus 1/4.
plus 1/4 equals 1. So what does x squared equal? How much? 3/4. And this time when you take the square root of the top and the bottom, you don't have to worry about fixing it because the bottom comes out nice.
Square root of 3/2.
Square root of 3/2. And that is how you find the length of the other side of a 30, 60, 90. Now that we know each side, let's label them. So this is root 3/2. That side is a half. So what do you think the coordinate would be for 30 degrees? Anyone think they would know? Rory?
I'm not sure.
So this would be 30 degrees right here. So there's 30 degrees. How far from the origin do you go right to get to 30 degrees?
Up 1 over 2.
Well, they're going to have square roots. They're going to have square roots in how far right you have to go. So we just solved for this. This is how far right you go, right here. How long is that side?
Square root of 2 over 2.
No, that's for the 45. Yeah.
Square root of 3 over 2.
Square root of 3/2. Okay, so the x was square root of 3/2. And then how far up do you go to get to 30 degrees? Yeah, 1/2. So that's the coordinate for 30 degrees. So 30 degrees is root 3/2, comma, a half. Well, now we just need the 60. Well, let's look at what happens when you draw the 60. Yeah.
Would it just be the 30 reversed?
Yeah, because when you put 60, what happens is the 30 and the 60 just switch places. So here's your 60. Draw your triangle. It's the same triangle that you just drew. The only difference is now the triangle is standing up instead of on the long side. So what's the bottom side that I just colored in blue? How long is that? Yeah. That's the 1/2. And how about the side that I just colored in red? Yeah.
Square root 3/2.
Square root 3/2. Exactly. So for the 60, it's 1/2 root 3/2. And the way you can remember which one is which, 1/2 is 0.5. Root 3/2 is about 0.866. Root 3/2 is a bigger number than 1/2. Root 3/2 is always the big side.
Bless you.
1/2 is the small side. All right. So as long as you draw your triangle, like 30 degrees somewhat accurately, you should be able to tell which side is the long side and then which side is the short side. Short side is always a half. Long side, root 3/2. All right, so if you can remember, there's really only two numbers to remember there. 3/2 and a half. And then there's one number to remember here. Square root 2/2. If you can remember those three fractions, you can do everything with unit circle trick. Root 2/2, root 3/2, and 1/2. Remember the root 2/2 is with the 45, and the root 3/2 and the half are with the 30s and 60s. Okay. And now that we've got those coordinates, I don't want to go through and find them again. I just want to remember those numbers. So let's try. Let's find the 6 trig functions of 45 degrees. Okay, if we're going to use the unit circle, what's the first thing you always have to know about an angle to do unit circle trig? Yeah, you got to know the coordinate. So hopefully we just get this from memory. What's the coordinate for 45? Yeah. Square root of 2 over 2, comma. Yeah. And the only thing that's going to happen when you have a 45-degree angle in a different quadrant is one of them becomes negative. That's the only difference. So when I say you should be able to do multiples of 45, a multiple just means one of these is a negative, or both, if you're in quadrant 3. Yeah.
Could you like use the numbers, like the fractions from the 30, 60 triangle to find like 85 degrees or 75 degrees? Because like it's 30 degrees away from the 45 location.
You can do something with 30s and 45s combined together to figure out a 75, but not something we're going to talk about for a little while. But yes, to do 15s, you need to be able to do these first, and then you can do 15s. It's a special formula. Yeah. All right. So what's the definition for sine? We haven't done this in a while. Sine is the
Y.
Y. Yep. Cosine
X.
is the x, which if you switch them, you'd be okay in this problem, but you really shouldn't switch them. And then the tangent,
Y over
y over x, which in this case would be 1. And once you get these 3, what do you do with them to get the other 3? Just find the reciprocal. So let's do the cotangent. That one's the easiest. What's the reciprocal of 1? Yep, just 1. And how about root 2 over 2? Does anyone remember what you get when you flip it and fix it? Yeah?
When you flip it and fix it, it'll just be the square root of 2.
Yep.
And it's for both of them.
For both.
They're the exact same.
Because they're the same thing. I think we did one similar to this in the homework. We did square root 2 over 2 as a coordinate. It was one I added on the board. I never explained where the root 2 over 2 came from, but now you know where it comes from. It's the coordinate for a 45. Any questions on that? So now we'll try either a 30 or a 60. I don't remember which one I have next. 30. All right. What 2 numbers are involved with the coordinate? I don't care if you put them in the right order. Just tell me the 2 numbers. Yeah. 1/2 and square root 3 over 2. So to figure out the order, what I do in my head is I imagine a 30. And I say, okay, 30 would be a little bit up from 0. And then I imagine what the triangle would look like. And I say, okay, that puts the long side on the bottom. That means the x is the big number. The y is the small number. So what's the big number in the 30, 60, 90? Yep.
Square root of 3.
That's the x. And what's the small number? That's the height of the 30. Yep. That's a half. Okay, that's a good thing to start being able to kind of visualize in your head, you know, where each side would be. Okay. How about the sine? That's going to be how much? Yep. Half. Okay, the cosine is going to be, yeah,
Square root 3 over 2.
square root 3 over 2. Okay. And how about the tangent? Yeah. Yep. Square root of 3 over. Anyone help her out? What's the tangent of 30? Square root of 3 over.
It would be the square root of 3 over 1/2, then you simplify it. Right? Because it's y over x.
So yeah, you got to simplify it as much as you can when you divide y by x. Yep.
So is it just going to be the square root of 3
Yep, because when you divide them, the 2's cancel, and you're left with 1 over the square root of 3. And then when you fix it, it becomes, so you divide them, you start with that, because the 2's cancel, and then multiply top and bottom by square root of 3. Now that we have both of those, we should be able to get the cotangent without any work. What's the cotangent? Right. I would just flip the first one because it's equal to the second one. But if you flip the first one, the root goes to the top and you're done. If you flip the second one, that's okay. But now you've got to fix it all over again. So square root of 3. Okay. The cosecant would be 2. And how about the secant? All fixed. Yep. 2 square root 3 over 3. Yep. So if you're starting to be able to flip these and kind of do that in your head quick, that's kind of the goal here. You want to be able to get this pretty quick. I mean, understand it first and then start doing it quick. Any questions on that? Okay.
So the sine is y, the cos is x, and tan is x over y.
Y over x.
Y over x, okay. And the other 3 are just the flipped versions of
Right.
x. Okay.
1 over y, 1 over x, and x over y. Yep, you just flip them. Well, what are they asking for here? The 6 trig functions, it's pi over 3. Well, what's pi over 3? Yeah.
60 degrees.
60. So this is pretty similar to the last problem. The last problem was a 30. This problem is a 60. So we can just kind of look at both and figure this out pretty quick. What's the coordinate for 60? That's where the triangle is up higher in the quadrant, so the height is higher than the base. Yep.
Well, for the one, the sin or the sine and cosine, the cosine will be 1/2, while the
So what's your coordinate?
I'm pretty sure that's y for the cosine, but for the x it's square root 3 over 2.
Square root 3 over 2 was the x value for the 30.
Wait, no, you gotta flip them, so it'd be 1/2 was the first one, and then
Yeah. So all that happened is the x and the y switch places. So all the x and the y switch places in the answers. Okay. So my sine is going to be 3 over 2. My cosine is going to be 1/2. And what's my tangent going to be? Yeah.
1/2 over square root of 3 over 2, and then you're going to
Square root of 3 over 2 over 1/2. 1/2 is in the bottom.
I thought it was y over x.
Y?
Oh yeah, square root of 3 over 2 over 2.
Square root of 3 over 2 over 1/2.
Each over half.
Yep. And what would that simplify to? Square root of 3. Right? When we flip 1/2, we get 2. How about when we flip root 3 over 2? Yeah. 2 root 3 over 3. And how about when you flip root 3? Yep. Square root 3 over 3.
So for these two, the sine and the cosine are flipped between them.
Those two flipped, yep.
Then the cosecant and the secant flip,
Those two flipped, yep.
but then the tangent and the cotangent flip.
Correct. What I just put boxes around, that's what flips between the 30 and the 60. That's what would flip between any two angles that were complementary. Yep. That's how it always works. So if you knew all the answers for 15, you should be able to get all the answers for 75 very quickly by switching what's in each set of the boxes. And what's in each set of the boxes, these are called cofunctions. Sine, cosine, secant, cosecant, tangent, cotangent. It's this function with the word co in front of it, called cofunctions. Okay, so that's 60. All right, let's try 135. So this is not in quadrant 1. This means we're going to be dealing with part of a coordinate that has a negative. Well, let's imagine what it would look like. Here's 90. Here's 180. You got to figure out roughly where the 135 goes. You really have three choices. It's closer to the 90, closer to 180, or right in the middle. Those are the three choices. Yeah, it's right in the middle. That's a 45-degree angle in the second quadrant. Every single angle that I give you on the unit circle is going to be a multiple of 30 or 45. That is a multiple of 45. It's not a multiple of 30. So this is 135, which means the triangle you just drew right here is the same as the triangle you would have drawn over here for the 45. It's the same triangle.
Wouldn't the x be negative and the y be positive?
Yeah, so when I label the lengths, they're both root 2 over 2, but when we write the coordinate, we're going left, so the x is negative. Yep. So negative root 2 over 2, root 2 over 2. That's all there is to doing the unit circle in another quadrant. That's why I said there's no new point you have to memorize. You just have to make something a negative.
Where did you get the square root of 2 over 2 from?
The Pythagorean theorem.
Oh, okay.
Yep. Comes from the Pythagorean theorem. All right. So what's my sine of 135? Yeah.
Square root of 2 over 2.
Yep. This time, if you mix up the x and the y, you will get it wrong because they are not the same. How about the cosine?
Just negative square root of 2 over 2.
Negative square root 2 over 2. And what about the tangent?
The negative 1.
Right, you're dividing two numbers that are opposites. That's negative 1. And I didn't do all 6. I just did the sine, the cosine, and the tangent. Any questions on the ones we did or how you would do the other three by flipping? All right. Let's try the sine, cosine, and tangent of 7 pi over 6. Now, what do you need first? If you want to do unit circle trig, somehow you got to figure out the what?
The coordinate.
You got to figure out the coordinate. If you need to change the degrees to get the coordinate, it's okay. Maybe that's how we should do it just to start.
210 degrees.
Yes. 7 pi over 6 is 210 degrees. It's 30 times 7. Okay, let's try. Excuse me. Thank you. Okay, here's 180. Here's 270. Where's 210? Closer to 180? Closer to 270? Right in the middle.
Closer to 180.
It's closer to 180. If it's closer to one than the other, it's not a 45 degree. It's the 30, 60, 90. 210 is not a multiple of 45. It's a multiple of 30. Okay, so draw your triangle. Okay, and I'll just color them so we can see them a little easier. Which side is the short side there? Yeah.
The red one.
The red one.
So the 1/2.
Yep. We'll take into account negative and positive when we write the coordinate. So the 1/2 and the green side. Yep. Square root 3 over 2. Now, the x and the y, when we write it as a coordinate, are going to be what kind of numbers? They're both what? Yeah, they're both negative. So the coordinate for 210 degrees on the unit circle is negative 3 over 2. Bless you. Negative a half. Okay. What's my sign? Yep.
Negative half.
Negative a half. Okay. What about my cosine? Yeah. Negative 3 over 2. And my tangent. Yeah.
Would that be root 3?
Over
3?
negative, yeah, it's root 3 over 3. Because when you divide, the negatives are gone, the 2's are gone, and you have 1 over the square root of 3, but then you need to fix it. Any question on that one? Okay, once you get it, I mean, you pretty much get it. There's not much more to it than what we're doing. I was going to do the calculator now. Does anybody have another question or want me to do one in quadrant 4? I didn't do an angle in that quadrant. What would be an angle you could do in quadrant 4 on the unit circle?
300, following up.
300 what?
300.
Yep, you could do 300, because that would be just a little bit past 270. That would be your short side. That would be your long side. What would be the coordinate for 300? Yep. Yep, 1/2 negative square root 3 over 2. And once you get the coordinate, nothing else changes. You just plug them all into the sine, cosine, everything they want to know. So on the unit circle now, you should hopefully start feeling pretty comfortable with the 0, 90, 180, and 270. Okay, those are the easy angles that all have the zeros and ones. You should be able to do the 45 in each quadrant. So all of the green dots would be root 2 over 2's for the coordinates. Might be both negative, both positive, or one of each. And then the blue dots are the 30 and the 60 in each quadrant. So those 16 points, you should be able to find the coordinates of any of those in the circle. You'll notice there are gaps. What we're missing is the 15s. The 15, the 75, and so on. We'll learn how to do the 15s later on. Not for a while. Okay. So any questions on how you find the coordinates of any of those points? All right. So what do you do if it's not a multiple of 30 or 45? Well, use the calculator. Okay. So let me show you how you type it in. Okay, first of all, what does that say? Yeah?
42 degrees.
42 degrees. Now, is that a multiple of 30 or 45? Either one. No. So you're not going to be able to get a coordinate for it. It's 42 degrees. So in order to type that in on the calculator, the first thing I have to do is switch my calculator to degrees. Okay, to do that, press mode, and then if you go down to the fourth option, you have radians, and then next to it you have degrees. Highlight degrees, hit enter, and once you do that, your calculator should say you're in degrees now. That's how you change to degrees. If it doesn't say degrees at the top, you're not in degrees. And then you just type them in. So we've got the sine of 42, cosine 42, and tangent 42. Those are the three answers to the ones on the left. And it said round them to 2 decimal places, so what do we got? 67, 74, and 90. Any questions on getting those three? Now, we don't have a cosecant, a secant, or a cotangent button. We get these exactly the same way we've been getting them all along. How are you going to get the cosecant?
1 over the sine of 42 degrees.
1 over the sine of 42. Exactly. How are we going to get the secant?
Same one.
1 over the sine of 42?
Oh, not sine, but where's the sine? Cosine.
1 over the cosine. Yep. And how are we going to get the cotangent? Yeah. 1 over the tangent. Notice I didn't type in 1 over 0.9. I did 1 over the tangent of 42. Why do you think I typed in the original trig function and not the numbers in purple? Yeah.
You rounded.
Yeah, because I rounded those. So it's better to go back to the original problem. So 1.49, 1.35. What was the last one? 1.1 something? 1.11. So any question on using the calculator to get the 6 trig functions at 42 degrees? Okay.
Is it cotangent x divided by y or is it y divided by x?
Cotangent is x divided by y when you're using the unit circle. But we did not use unit circle in that last problem. Because we can't.
So then I would put that in, what exactly would I put in on the calculator of cotangent?
For cotangent, you want to do 1 divided by the tangent. Remember, the 3 on the right are just the reciprocal of the 3 on the left. Okay, somebody read this to me. What does that say? Yep. Sine of 10 radians. How do we know it's radians?
It doesn't say that it's in degrees. So
Exactly.
It's got to be in radians.
It doesn't say it's in degrees. It doesn't say degrees, then it's radians. I won't tell you that on the test. You need to know reading that that's 10 radians. Same thing, now just type it in. Sine of 10 and cosine of 10. So negative 54, negative 84.
You don't have to close it, is it? Well, it doesn't matter.
No, it doesn't matter because there's nothing coming after it. If you had more you needed to do in the problem, like sine of 10 plus 1, well, there's a big difference if you do the sine of 10 plus 1 or you do the sine of 11.
Yeah.
That's different. Yep. And then if I wanted the cosecant and the secant, how would I type in cosecant for this problem? Yep.
Oh, 1 over sine of 10.
1 over the sine of 10 radians. Yep. Any question on that? Okay. So we keep seeing this connection between sine, cosecant, cosine, secant, tangent, and cotangent. And the connection is that these are what we call reciprocal identities. That means that you flip one to get the other. And because it's an identity, it's true all of the time. It's not like it only works if the angle is 10 degrees. It works for any angle you want to do. Now, these are kind of redundant. It's really the same thing. Right? If you think those two equations are different, then it's kind of like saying that these equations are different. No, they're not. They're not really different. They're the same equation, just rearranged different ways. And when you have a fraction equal to a letter on the other side, you can always switch what's in the bottom and what's on the other side to get a different version of it. Okay? So this is saying if you flip the sine, you get the cosecant. Well, the next one is saying if you flip the cosecant, you get back the sine. And same thing here and here. If you flip cosine, you get secant. If you flip secant, you get cosine. If you flip tangent, you get cotangent. If you flip cotangent, you get tangent. It's exactly how we've been doing the reciprocals all along. I'm just kind of making it a little bit more formal and saying that these are what we call reciprocal identities. And what can you do with that? Well, let's say you had something like this. Cosecant times sine. What did we just say cosecant was from up above? Yeah. Cosecant is 1 over sine. So what would you get if you multiply the cosecant by the sine? 1. Exactly. And that's a huge thing we do in trig. That's called simplifying a trig identity. So in calculus, if you had to do something with this, it's a lot easier to think of that as just being the number 1 than cosecant times sine. So that's taking an identity and simplifying it. You don't have to understand that in depth right now, but that's kind of where these identities start to come in. They allow you to simplify trigonometric expressions. Any question on that? All right, so let's take a look at a couple special properties about sine and cosine. This is going to kind of lead us into, we'll talk more about it tomorrow too. Here's what the graph of sine looks like. Type it in. Well, does anybody already know what it looks like?
Yeah, it's like a wave that goes up and down.
Yep, it's a wave. And if you zoom out, it just keeps looking more like that. So if we wanted to talk about the domain of that, how far left and right do you think that graph goes? Yeah?
For infinity.
Yeah. It just keeps going left and right forever. Right? If you set the x max higher, all you're going to do is you're going to see more waves. But it just continues like that forever. And how about up and down? What does it look like the range is for sine?
1 and -1.
Yeah, and cosine is the same thing. In fact, there's a pretty close connection between sine and cosine. What transformation do you think you could use to describe them?
Horizontal shift.
Yep, they are horizontal shifts of each other. In fact, they're exactly a horizontal shift of 90 degrees. One of them is 90 degrees off from the other. Okay, we're going to study more about the graphs tomorrow, but
What do you mean?
so each, if I go back here, each tick mark, let's see how we can set it up. Let me do something here. Let me go sine, cosine, let me put it in degrees. You do zoom 7. Each tick mark here represents 90. So that's 90, 180, 270, 360. If you shift the graph of sine or cosine exactly 1 tick mark, it would line up with the other one. That's what I mean. Can you see how if you shifted it 1 tick mark, it would line up? Yeah, and each tick mark represents 90 units. And how do I know it represents 90 units? Because it says the x scale is 90. So each tick mark is 90. All right, so now let's try something. We did the sine of 42. Okay, we did that earlier. What did we get? 0.67. Okay, so let me do that. Now let me do the sine of 42 plus 360. Does anybody remember what happens when you add 360 to something? You get an angle and there's a special name. Yeah?
Coterminal.
It's coterminal. And whenever you have an angle that's coterminal, the trig function comes out exactly the same.
Basically in the same spot.
It's in the same spot on the circle. You're just going around an extra time. But this doesn't care about how many times you go around. It cares about where the point is on the circle. So what do you think I would get if I did sine of 42 plus 720?
It would just be sine of 42 because the 720 doesn't matter.
Yeah. What about sine of 42 minus 360?
That
Same thing.
Same thing. Okay. You're just going around
it's just
more times.
one entire rotation.
Now, we did,
Whether it's 9 or 4 cos.
yeah. Now we did 10 radians as well. Sine of 10 radians. What could I put inside the parentheses there and make it come out the same? Yeah?
Well, you could put sine of 370 or sine of 360.
2 pi.
2 pi, yes.
Oh, why? Because we're in radians now.
Because we're in radians now. All right, so if you add 2 pi, it comes out the same. What if I did 10 plus 4 pi?
Same thing.
Same thing. I'm just adding more revolutions. So you can add or subtract 360 degrees or 2 pi radians as many times as you want. And adding or subtracting multiples of 2 pi will give you the same answer as what you have right there. It won't change the answer. Okay, that's called the periodic property of sine and cosine. And the idea on the graph is, let's say you're right here on the graph. If you go 360 degrees down the graph, you're going to be in exactly the same spot in a different cycle. Okay. And because you land in the same spot in a different cycle, that's why you get the same answer. Because remember what sine is. Sine's like the y value, right? It's like the height. These 2 points are at the same height if you drew a line right there. That's the idea. So any question on that idea? Oh, adding and subtracting. N is just an integer. So you could add 2 pi times 1, 2 pi times 2, 2 pi times 3. You can't add like 2 pi times 0.6.
Can't.
You have, yeah, you got to go a full revolution. So you can add 1 revolution or you can add 2. You can't add anything in between. It has to be an integer.
It's something about that earlier because you were dividing for when you were finding like the angles and stuff. You were like free to find the cosecant, secant of the angles. If they had like pi in them, or like they were like fractions. Like how would you like solve that out? Like for the for 60 degrees is like 1/2 square root of 3 over 2. Free to find the like the cosecant of that, the 1 over square root of 3 over 2. How would you solve it out?
So you're trying to find the cosine of 60 degrees?
Yeah, but like how like I know like the formula for it. It's just how do you solve like a fraction on top of a fraction mathematically?
Oh, well, so if you have 2 fractions like this.
Yeah.
So to divide 2 fractions, you keep the top the same, multiply by the reciprocal of the bottom.
Oh, thank you.
Yeah. Except we do it with square roots most of the time.
And that would still work if it was square roots.
Oh yeah. Yeah.
Thank you.
Yeah. You just have to simplify the square roots because you're not allowed to leave a square root in the bottom of a fraction. Yeah. Yep. Keep the top the same, change to multiplication, flip what's in the bottom. All right. And yeah, we'll get the last thing. All right. So the last thing we're going to look at is something we're going to spend a lot more time on, I think, either later in chapter 6 or chapter 7, and that's all kinds of different trig identities. I've already shown you 6. First 6 I showed you were what we call the reciprocal identities. So remember that an identity is a formula that is true all of the time. It's like a Pythagorean theorem. It works all of the time. It doesn't matter if one side is 2 and the other side is 9.7. It still works, as long as it's a right triangle. So there are different categories of identities that you're going to learn that you kind of have to have a pretty good understanding of to be able to do calculus. I'd say the reciprocal identities are very important. There's another group called the Pythagorean identities. I'm not going to go over those today. And then another group would probably be what we call the quotient or the tangent and cotangent identities. Those are 3 basic groups. There's other ones too. We're going to study ones called sum and difference identities. We're going to do double and half angle identities. It's all different ways to basically change a formula that has trig in it, usually to something similar. That's kind of the goal. So the first group of fundamental trig identities are the reciprocal ones. You guys already have these written down. Okay, so you don't have to write them all again. But that's the first group. Okay, I'm going to give you one more group of identities. There's only going to be 2 in this group, though. This group had 6. If you count them all different, I really just count it as 3. You've already kind of seen this idea. Okay, think about when we did the unit circle. This is the connection. What was sine?
Y.
Sine was the y. What was cosine?
X.
X. And what was tangent?
Y over X.
Tangent was y over x. Well, we just said that y is what?
Sine.
Sine. And what did we say x is?
Cosine.
Cosine. So really, even though you might have not known you were doing it, you were doing the tangent and cotangent identities. Tangent is defined as the sine divided by the cosine. So if you took, just make up, I don't know, tangent of 5 radians. Well, if you took the sine of 5 and you divided by the cosine of 5, you will get exactly the same thing. Because tangent is always sine divided by cosine. Now, if tangent is sine divided by cosine, what would you think the cotangent would be? Yeah.
Cosine divided by sine.
Yeah. Cotangent is the reciprocal. And don't worry about the Pythagorean identity. We're not going to do that. And you've been doing that all along when you find cotangent. Think of the formula we've been using. Cotangent is x divided by y. Well, x is cosine, y is sine. So cotangent is always x divided by y. Okay. Now let's take that one. Let's say you had sine squared over cosine squared. What does sine squared mean? Like if you write it out. Yeah? I mean, just don't change it to unit circle. Just expand that for me. Yeah?
Just sine times sine.
Means sine times sine. What does cosine squared mean?
Cosine.
Yep. It means cosine times cosine. Now, think of that as 2 fractions. What's sine divided by cosine? That's tangent. And what's sine divided by cosine again? And what do you think tangent times tangent is? Tangent squared. I'm going to show you how they write tangent squared. They usually don't put the 2 on the outside. This is how they usually do it. It's a notation thing. But tangent squared if you had to do it on the calculator, you do have to put it in like this. On paper, though, that's how people write. So sine squared divided by cosine squared is tangent squared. All right. So then, without going through all of that, what do you think sine cubed over cosine cubed would be? Yeah. Tangent what? Tangent cubed. So the point I'm trying to show you here is these identities work for higher powers. Technically, you could have sine to the n as long as it's cosine to the same power. And then you get tangent to that power. Same thing here. And same thing with all these ones up at the top too. If you flip the cosecant, you get 1 over sine. What do you think you would get if instead of just flipping the cosecant, you flip the cosecant squared? Well, think about this. What's this? When you flip the cosecant, what do you get? Sine. Okay. When you flip the cosecant, you get the sine. So what if you flip the cosecant squared?
Sine squared.
Sine squared. If you flip, let's just try one more. If you flip the cosine, you get secant. So flip the cosine, gives you the secant. What if you flip the cosine squared? What do you think you get? Yep.
Secant squared.
Secant squared. Yep. So all of these identities that I wrote down up here, you could really put an exponent of n on all of them. If you flip cotangent to the 10th, you get if you flip cotangent to the 10th, you get tangent to the 10th. If you do 1 over secant to the 5th, you get cosine to the 5th. Okay, whatever power you're flipping, that's the power that ends up in your answer. We don't generally do a lot that have powers higher than 2. But you can use them for any power that you want. Okay, does everybody have the tangent and cotangent? And the reciprocal, you already had those. You just add in the n for the power. That, I'm going to save that. Work for higher powers. This I already explained to you. If you want to write that down again, you can, but that's what we already said. So let's try an example. I want to simplify that. Cosecant times tangent. And I'll tell you the trick that you use to simplify it is to change everything that you can to sines and cosines. Start with cosecant. What is cosecant? In other words, how would you do cosecant on the calculator? The way we've been doing. Yep.
1 over sine.
It's 1 over the sine. Yep. And how about tangent? How can you rewrite that? So it has sine and cosine in it. Yeah.
Sine over cosine.
Sine over cosine. Now think about what's going to happen when you multiply there straight across. Yep.
It would just turn to a secant or 1 over cosecant.
Those are going to cancel out.
Sine.
Because whenever you're multiplying, you have the same thing in the top and the bottom. And then, can you explain what do you have left here, and then
It would
explain?
It would be 1 over cosine, which would be equal to secant.
Perfect. Exactly. So now the whole point is we started with two trig functions that were multiplied together, and we found a simpler way to say that. This is just the secant. And it's a lot easier to work with just secant than cosecant times tan. Question on it? Yeah.
Are we gonna have to like memorize all these? Like be able
Well,
to
the reciprocal ones you should already know. 1 over sine is the cosecant, 1 over cosine is the secant, and 1 over tangent is the cotangent. Because we've been doing those with unit circle trig. So the only thing that's really new is the idea that sine over cosine gives you tangent. So, and even that, we've been saying y over x is always the tangent, and that's exactly what this says. So there's not really any new concept here, just looking at it a different way. Let's try this one. What's the secant?
1 over sine.
What is it? That is 1 over cosine. And cosine, it's not a fraction, but you could think of it as 1 if you want, like that. What do you get if you multiply those together? I kind of did one like that earlier. Yeah, you get 1. So sometimes when you simplify a trig identity, the whole thing just turns into a number. That's very easy to work with. Not often. Most of the time, it simplifies to another trig expression that's just smaller. Okay, let's try one more. Okay. Cotangent divided by cosecant. I want a simpler way to say that. Well, what's cotangent? I'm looking for a way to describe that in terms of sine and cosine. That's always the goal. Change everything to sine and cosine. Yeah? That's cosine over sine. And what about cosecant? How can we write cosecant? If you're going to type cosecant in on the calculator, how do you do it?
1 divided by the sine theta.
You flip the sign. Okay. Now, how do I deal with that? Yeah.
I know the answer to the full equation, but how would you simplify it more from there would be to take the top equation, just bring it on down, then multiply it by sine over 1, which would equal cosine.
Equal. Exactly. So instead of writing cotangent divided by cosecant, a much simpler way is to just say the cosine. Any question on it? So I don't expect you to be super good at simplifying these identities yet. It's something we're going to spend at least 2 or 3 more classes on. But this is just kind of like a little bit of an introduction to doing it.
That's real.
Thank you.
So that's the homework for tonight. The 335 is all unit circle, the numbers at the top, and using the calculator. And then there's one trig identity that I want you to try to simplify. Secant squared divided by tangent squared. But you will need a calculator to do a good amount of the problems on home. Also, pay attention in the directions. If it doesn't say to find all 6 trig functions, you don't have to. Just the ones that it asks for.